Today we're going to work on solving inequalities. This is section 2.8. This is something we should have some practice in, but we're going to take this a step further today. So the first example we're going to work with is 3x minus 6 is greater than or equal to 0. For something like this, hopefully we'll practice in adding the 6 over, dividing by the 3, and we get infinite many solutions. X is greater than or equal to 2. We should represent this infinite amount of solutions using interval notation there, 2 to infinity. We're going to look at this a little bit differently though. What if we had some function and we called it 3x minus 6? And I asked, when is the function greater than or equal to 0? What we should be thinking of there graphically, when we compare a function to 0, we're comparing a function to the x-axis. So what we're saying is, when is this function above or on the x-axis? To do this, we would look at the image of this graph. This graph is a linear function with a y-intercept of -6, a slope of 3. So we're going to cross the y-axis at 2. And here what we would be looking for is above or on the x-axis. We're on the x-axis at 2, and then we're above the x-axis from 2 out. We would say our solutions would lie from 2 to infinity. We're going to hold on to that as we move forward with our future problems. The second example that we're going to look at today is a factored function. This function is f of x, which equals x plus 3 times the quantity x squared plus 1 times the quantity x minus 4 squared. And the question I'm going to ask you here is solve for when f of x is greater than 0. For us, greater than 0 should mean above the x-axis. So in order to do this, one thing we can look at is the image of this graph. This graph is going to be a 5th degree polynomial. We've got a 1st degree times a 2nd times another 2nd. We've got a 5th degree polynomial that's going to cross the x-axis at -3. It's also going to cross the x-axis at +4. And actually, to be more precise, we're going to bounce off the x-axis at +4 because of the multiplicity, the duplicate x minus 4 factor. So this would be the image we're looking at. And we're going to go back to, when is this graph above the x-axis? This graph is above the x-axis between -3 and 4, and also from 4 to infinity. We're not going to include -3, we're not going to include 4, because at those places the graph is on the x-axis. How do we solve something like this algebraically? When we've got a function, or an expression now if we remove the f of x, and we want this expression to be greater than 0. Well, one thing we can do is look at the left side and create a function and look at when is this function above the x-axis. The other thing that we're going to learn today, the algebraic technique, is going to be called a sign pattern chart. And for this sign pattern chart, we always must compare to 0. And the reason we compare to 0 is because we're going to worry about negative, we're going to worry about positive, and we're going to worry about 0. Those are only relevant when we compare to 0. So I'm going to do a sign pattern chart. And for this sign pattern chart, I'm going to determine when this expression is equal to 0. Well, this expression is equal to 0 at -3. This expression is equal to 0 at 4, and nowhere else. So I'm going to say at -3 and 4, I have 0 values. I'm then going to look at each factor independently and determine the sign of that factor on this interval. So if I look at x plus 3, on the interval from -infinity to -3, if I plugged in a number over here like -4, I would get a negative number. But if I plugged in a number between -3 and 4, for the x plus 3, I would get a positive. And then from 4 and bigger, I would get a positive for that first factor. The second factor of x squared plus 1, that's always positive, no matter what the x value. The last factor of x minus 4, that would yield a negative number, but I need to square that. Between -3 and 4, that would also yield a negative number, but I need to square that. From 4 to infinity, I would yield a positive number. Again, that's squared. So I'm going to look now at a summary of a negative times a positive times a negative squared, and that will yield a negative. A positive times a positive times a negative squared will yield a positive. Positive, positive, positive squared will yield a positive. Let's go back to the problem. The problem asks, when are we greater than 0? We had talked about that meaning above the x-axis. Greater than 0 is also code for positive. So I need to look down below and see the intervals where I yielded a positive on this sign pattern. The two intervals would be from -3 to 4 and from 4 to infinity. This is an algebraic technique. We should be connecting the graph and the algebraic technique here, but the algebra helps us solve this inequality that is higher than a first degree. Keep in mind we are comparing to 0. Keep in mind we are using factors here. In example 3, we're going to use a function g of x. G of x will be a third degree polynomial, 2x cubed minus 7x squared minus 10x plus 24. And I'm going to tell you a little bit of information here. I'm going to say given g of 4 equals 0. The question I'm going to ask is this. Solve for g of x when g of x is greater than or equal to 0. I'm going to do this purely algebraically. In order to do this algebraically, I need to have 0 on one side of my inequality. So g of x needs to be greater than or equal to 0. I've got that. So the problem that I'm solving is this. 2x cubed minus 7x squared minus 10x plus 24 needs to be greater than or equal to 0. The other piece I need is I need factors. Well, fortunately, I was given a starting point to help me factor a 4. I can use synthetic division to help me find the other factors. Carry down the 2, multiply by the 4, add down, multiply by the 4, add down. Hopefully I come out to have a remainder of 0, which I do. I've now said that x minus 4 times the quantity 2x squared plus x minus 6 needs to be greater than or equal to 0. Let's factor that further into 2x and x. One of these signs needs to be positive, one of them needs to be negative. Let's go with a plus 2 attached to the x and a minus 3. That would give me my plus x in the middle. I'm now going to do a sign pattern for each of these factors. I need to determine when does x minus 4 equal 0? Well, that occurs at a 4. When does 2x minus 3 equal 0? That occurs at a 3/2. When does x plus 2 equal 0? That occurs at a -2. I'm now going to consider the sign for each of these factors, starting with the x minus 4. X minus 4 will yield a negative number until I plug in a value bigger than 4. 2x minus 3 will yield a negative number until I get bigger than the 3/2. And x plus 2 will equal a negative until I get bigger than the 2. I'll now summarize each of those intervals. 3 negatives will yield a negative. 2 negatives will yield a positive. 1 will yield a negative. And then all positives will yield a positive. Let's go back to the question. The question asks, when is this expression going to be greater than or equal to 0? Greater than or equal to 0 should be positives or 0. So down below on my sign pattern, I have a 0 at -2. I have a positive. I have a 0 at 3/2. I have a 0 at 4. And I have a positive from 4 to infinity. So if I were to write this final answer in interval notation, I would say from -2 to 3/2, union 4 to infinity. I'm including all of those values because 0 is good for me. Let's remember the graph of this function. This is a cubic. It's a cubic that crosses the x-axis at -2, at positive 3/2, as well as at positive 4. Normal end behavior for a cubic. When is this function above or on the x-axis is what we're looking for, because we were told to be going from a greater than or equal to 0. The final function that we're going to look at today is a rational function. So example 4, we'll call this r of x. R of x equals 2x plus 1 in the numerator, and it equals x squared plus 2x minus 3 in the denominator. The question I'm going to ask is solve for r of x, which is less than or equal to 0. I would like to factor anything that's factorable here, which is the denominator, x plus 3, x minus 1. And now I'm going to do a sign pattern for each of these factors. When do each of these factors equal 0? The numerator factor of 2x plus 1 equals 0 at a negative 1/2. The denominator equals 0 at negative 3. That will actually yield an undefined because we're dividing by 0. The denominator also equals 0 at positive 1. That will also yield an undefined. I'm now going to do a sign pattern for each of these intervals. The numerator will equal a negative until I get bigger than negative 1/2. And then I'm going to yield a positive. The denominator of x plus 3 will yield a negative until I get bigger than the negative 3. And the other factor of x minus 1 will yield a negative until I get bigger than the positive 1. Now I'll do a summary here. Similar to the multiplication, negative divided by two negatives will give me a negative. Negative divided by a single negative will give me a positive. I'll get a negative over my next interval, and then I will get a positive. So what did the question ask? The question asked, when are we less than or equal to 0? This should be code for when are we negative or 0. So down below on my sign pattern, I'm going to look for negatives. I'm going to look for zeros, and those are going to be my locations. I'm going to turn this into notation. I'm going to have a negative value from negative infinity to negative 3, not including negative 3. And then I'm going to include negative 1/2 because a 0 value is good. All the way up to 1, I'm not going to include that 1. I would challenge you to compare this sign pattern to the graph. How would this graph look in comparison to what we're getting out of this sign pattern?